So one of the most important parts about amino acid metabolism and breakdown of amino acids is to actually remove the nitrogen group. And that process is a deamination event. What that is dependent upon is that's dependent upon vitamin B6. And vitamin B6 has a couple of different forms. It has this pyridoxine, pyridoxamine phosphate, and there's another form of it that is pyridoxal, DOXAL. These are all, I'm going to use arrows to take all of them, and this. These are all precursors for this molecule right here, pyridoxal 5-phosphate, PLP. Now, PLP is a primary cofactor in one of the major deamination reactions of amino acids. And what that molecule is going to be involved in is, well, it's going to form a covalent linkage with our enzyme, our deaminase or transaminase reaction, or transaminase enzyme that's catalyzing that reaction. So the first step in amino acid breakdown is a transamination reaction. So I'm going to start up here where we have our alpha amino acid. Now this is just a general amino acid. I'm not specifying which one. The reason for that is all your amino acids are going to undergo the removal of this, what is the N-termini of the amino acid. So our alpha amino acid are our proteinogenic amino acids. They have an R group, they have an alpha carbon, and from that alpha carbon we have our N-termini. And this is the group that we want to remove. What we're going to have to do is we're going to have that pyridoxal, DOXAL 5' phosphate, and what we're going to have between that pyridoxal 5' phosphate and our enzyme is we're going to have a covalent linkage between our enzyme and this group right here. So we're going to have a covalent linkage with that, and this is just classified, or this is just written as enzyme due to the fact that different amino acids are going to have unique transaminases. So there's a different transaminase for something like glutamic acid as there is for arginine. With that said, though, they're catalyzing the same reaction. Okay, so when we have that present, what we're going to do is we're going to, in our very first step, move the electrons that constitute that double bond over to our positively charged nitrogen. Move those electrons over there, and this nitrogen right here will have also picked up one of our hydrogens from our alpha amino acid. Those then formed a bond between our alpha amino acid and our enzyme PLP shift base. The lone pair of electrons that exist between our N-termini of our amino acid and this carbon, well, we're going to form a double bond between the alpha amino acids N-termini and our PLP shift base. And now what we're going to do is basically have this amino acid, our alpha amino acid, right here, more or less replace the enzyme, and we're going to be forming this amino acid PLP shift base. What is then going to give us is an enzyme that has a side chain residue that has an NH2. Okay, now that NH2, well, let's think about what the identity of this group is here. I always like to look at the amino acids, and I always like to think about their protonation state. Okay, so what we have here, and I'm going to go ahead down here, and we're looking at our enzyme's amino acid R group. We've got CH2, we've got 4 of those, followed by NH2. Okay. Now, what R group is this? Well, this is going to be a K, or a lysine. Okay. Now, what do we know about the pKa of this group? Sorry, that's supposed to be a lone pair of electrons. What do we know about the pKa of that group? Well, it's fairly high. That pKa is something like pKa equals, let's call it 10.5. So at a physiological pH of 7, this group is definitely going to be protonated. So what it's going to do is pick up another proton to give us our positively charged lysine. And I know that you probably could have simply looked, rather than following my writings, you could have just looked down at the bottom and said, oh, well, it says LYS, that's a lysine. But I always like to think about the amino acid R groups and think about their side chains, what those side chains look like at different pHs, and, you know, just use kind of context clues to deduce what that is. So ultimately, what we've got here is a resonance stabilized intermediate where we have now a lone pair of electrons and a negative charge on this our alpha carbon, because that alpha carbon gave up, and I'm going to highlight it, this hydrogen right here. And when it gave up that hydrogen right there, our lysine residue became protonated. So when you think about the fate of this, well, this is ultimately, we want to regenerate our enzyme PLP shift base. We want to get back to this. We're not there yet, but just kind of foreshadowing, we want to get back to that. We want to reform that structure right there. But what this gives us is our N-termini of our alpha amino acid now has a double bond to our PLP, and so we've got this molecule we've got this resonance stabilized intermediate that we can begin, or we can continue moving towards the total deamination or transamination of our alpha amino acid. So in this, what we're going to do is we're going to take off from where we most recently were. We have our protonated amino acid, or protonated enzyme. We have this resonance stabilized intermediate, which our former alpha amino acid is now linked up with our PLP. Okay. What we're going to do after that, or a movement away from that resonance stabilized intermediate, is going to take us to this imine and this amine, which are tautomers of one another. Now, in order to get there, what we have to do is we have to deprotonate our enzyme. Our enzyme is going to give up the hydrogen to this carbon right here. While that happens, we also have a hydroxide group that's going to come on, and with its lone pair of electrons, form an OH with this alpha carbon. That's going to push the electrons that were in that double bond down to the nitrogen, which was our original nitrogen from our alpha amino acid, and that will give us our carbanolamine. Okay, so we have this inner conversion from this imine-amine form of this molecule. Okay, now one good thing to keep track of is we've got our deprotonated enzyme ready to go. And the deprotonated enzyme is kind of the first step along the way of getting us back to being able to catalyze this reaction all over again. So now what we have is basically our third step in the transamination, and arguably the most important part about this whole process is what we wanted to do was we wanted to get rid of our, I know, so, okay, wait for me. What we wanted to do was we wanted to transfer our N-termini of our amino acid basically away from it. And so our third and final step is taking this carbanolamine and releasing our alpha keto acid. And by doing so, we now have, rather than a PLP enzyme, we have a PMP enzyme. So pyridoxamine phosphate. We've transferred our N-termini of our amino acid onto our vitamin B6 or our pyridoxamine molecule, or pyridoxal molecule. So this gets us to a point where we've generated one of our products. Now this PMP, oh wow, this PMP can be used to transfer this NH2 onto something else. So we've done, you could think about this, I know, we can look at this as we wanted to transfer our nitrogen away from our amino acid. We can consider that done at this point. All right, well, thank you very much, and we'll see you in the next video.